Thanks for hosting, Sophia, and thanks for the introduction. So today I'll give a talk about graph neural networks for skillful weather prediction. And as the subtitle says, it's basically going to be two stories. I'm going to aim for about 25 minutes, and I'm going to tell them in 3.5 papers. The first one is one I did in my PhD, which is it was in a TOEIC problem, but it's going to set the setting and also talk about like the basic components of what graph neural networks are and how they could ever be applied to weather prediction. The second one is GraphCast, a paper we did at DeepMind on basically scaling these and using graph neural networks for state-of-the-art weather prediction. And the GraphCast was kind of deterministic, so only predicting the average of what's going to happen, making a single prediction. And late last year, we've recently made a probabilistic version of this using diffusion models. But of course, I said 3.5 papers. The reason is that basically, if we think about the two topics, there's also going to be another extra paper, which is Science GraphCast. Basically, it took us 6 months to go from GraphCast to Science GraphCast, so I'm also going to talk about this. The two stories are going to be, the first one is structured in machine learning. So how and when do we want to build inductive priors into our models? And the second one is going to be about impact in machine learning. So how does impact look from academia? How does impact look in industry? And maybe how this has evolved over time. So let's start with the overall setting. So the motivation is that, as we all know, inductive biases play a role in machine learning. So for instance, convolutional neural network are a useful inductive bias because they exploit structural properties, like in this case, locality and shift invariance, that are satisfied in a broad set of computer vision tasks, for example. Then we have, for instance, graph neural networks, which again are a useful inductive bias because in this case, the structural property is the fact that entities exist in the world, there's objects or there's different people, and that when you model them, they're permutation invariant, and that these structural properties are satisfied in a broad set of tasks. In this case, when we model entities and their relations. So for instance, the early graph neural network works were modeling web pages or citation graphs. Then people use them to model molecules or proteins in some cases. And there's also been work in using them to model physical interactions. So for instance, bouncing balls, or other types of objects interacting. In our case, we were interested in modeling what I called spatial function transformations. Now, people sometimes call them neural operators or other types of names or functa. So imagine you have a metric space, in this case, the Earth, and you want to, you care about two types of functions. The first one is an input function, like for instance, the humidity and wind today. And the second one is an output function, like for instance, the rain tomorrow. So we have two functions, f and g, and our goal is to map a function f to function g. So we take a function that goes from x to y and output a function that goes from x to z. But in practice, we're going to have samples of both functions. It's important to know that usually in machine learning, we learn a single function, right? We map from, for instance, images to objects in those images. In this case, though, we have a function of functions. So our data set is going to map, kind of create a data set of functions. So for instance, the weather of January 1st, and then the weather of January 2nd. Then from the January 2nd, we have to predict January 3rd, and so on and so forth. And then at test time, we're going to receive an input function like humidity and wind today. And we're going to receive one or more queries, and we have to predict the weather on those locations. So if we think about inductive biases, what properties are satisfied in these function-to-function transformations, we could take insights from partial differential equations. If we think about a partial differential equation, the initial state of the partial differential equation may be the input function, and the last state of the partial differential equation, we can think about it as the output function. So from this perspective, if we look at these equations, there's multiple things that we can notice. Don't worry about the explicit symbols. We're just going to look at them kind of in general. The first thing is that the same equation is applied everywhere. If you can see, that the equation does not depend on x and y. It's applied, the same function applies everywhere in the domain. So similar to images, for example, this is going to be translation equivariant, meaning that the same function applies in all places on Earth, for instance. The weather physics are the same here in London and maybe in California. The second thing is that the composition of local functions. So for instance, the derivatives here are going to be local in time and are going to be composed. And also we have derivatives in space, which are by definition local. So this suggests something like a deep GNN. The third thing is that the same function is always the same. So basically the weather today, the physics of the weather today are the same as the physics of the weather tomorrow. Physics don't change. So we got inspired by finite element methods, which are widely used in science and engineering. And the idea is that we can decompose the space into small regions and model that and basically embed the problem into a graph. There's two nice things about this. The first thing is that we can have small decomposition with lots of regions or very few decompositions and into very large regions. And this essentially trades off compute with accuracy. If you want to spend more compute, you can do a better job. The second nice thing is that we can focus compute where it matters. So if there is a boring region, we devote very little nodes to that. And if there's an interesting region, we devote a lot of nodes and compute to that. So if we think about what this paper is telling us, is that the structure in machine learning in this case is that we can use graph neural networks. And the impact of this paper was suggesting that graph neural networks could be used into a new setup, right? Instead of modeling discrete entities, we could use them to model function-to-function transformations. So if we think about this, we have a metric space and input samples and output queries. And now we want to map from input to output. So more precisely, how does it work? Well, as we usually have in deep learning, we encode into a latent space, and then we decode into the final output. However, if we were only doing this, our transformations would be local, right? Like, for instance, a hurricane today in Cuba could not affect the probability of a hurricane tomorrow in Miami. So we have to propagate this information. And the way we're going to propagate the information is using graph neural networks. So essentially, we first use attention to initialize the nearby nodes in the mesh. And then the mesh is going to propagate the information via message passing of using graph neural networks, standard graph neural networks. I'm going to talk about it more in a second. And then once the nodes and the graph has been updated and the information has been propagated, we can then run the attention in the reverse direction and make the final predictions on the locations we really care about, and then finally decode. If we think about the parameters of this model, we have a neural network in the encoder, one in the decoder, and then we have edge and node neural networks, which are typical in graph neural networks. And the key important thing is that edges and nodes are reused across all edges and all nodes in the graph. So basically, we can reproduce the same parameters are reproduced as many times as needed. The nice thing about this is that we can essentially create as many nodes or as few nodes as we want. So we can have a very small graph to go very fast or a very big graph to go and be very accurate. A bit more subtle is that compared to previous graph neural network work, we are also creating the graph. No one has given us the graph, right? We have transformed a function problem into a graph problem, meaning we invented the nodes. We can put them wherever we want. And in particular, we can train them via gradient descent. In this case, as I was saying, it's a kind of academia paper. The experiments were kind of relatively small. So we learned to solve a partial differential equation. For instance, you get the boundary conditions, think about temperature in the walls of a room, and the Laplacian, which is think about, like, for instance, where there are heaters in the room. And then finally, you can predict the temperature everywhere in the room. So what we showed in that paper is that you can trade compute and accuracy similar to finite element methods. So if you have a very small graph, you get not so good accuracy. But with the same parameters, you can build bigger and bigger graphs, and performance and error keep going down. The second thing is, again, how we can focus on harder regions. And you can see that the nodes are focusing in the most interesting places of the space. And that leads to even better performance. Let's now look into GraphCast, which was a paper that we published at DeepMind. We're first going to talk about the archive version. So the goal of that work is predicting the Earth's surface and atmospheric weather up to 10 days ahead, and at 0.25 degrees latitude longitude resolution, which you should think about like a 30 by 30 kilometer grid. So one prediction by every 30 by 30. We are making predictions about wind, we are making predictions about surface temperature, but also predictions about any place at different altitudes in the atmosphere. So for instance, temperature at 500 hectopascals, which is a measure of kind of altitude. But here I'm only showing 3 out of more than 200 weather variables that we were modeling. The intuition is that machine learning can learn better approximate physics. So how this was done until now, and still now in some weather agencies, is essentially we know roughly the laws of physics, right? In practice, though, we have finite compute and we also have noisy data. So we're going to make approximations of those physics. So hopefully, even though the laws of physics, we mostly know them, these approximate physics and working with noisy data, machine learning maybe can find a better way through that. In particular, we are competing, usually in machine learning, we compete against other machine learning papers. In our case, our goal was to improve upon a physics model that has been developed over decades. One thing that may not be obvious is that weather outputs are very, very large for machine learning standards. So if we look at our model GraphCast, it works at 0.25, so it's a very high resolution image. So if we think about MNIST, this is a bit of a depiction, but I think the scales are roughly right. We had MNIST, we have ImageNet, and then we have a single variable of ERA 5, which is our data set that we use, created by the European Weather Agency. So the image is already larger than the ImageNet images, but in ImageNet, we have 3 channels. We are predicting R, G, and B. In our case, we have more than 200 variables that we're predicting, so there's going to be a much richer image. Furthermore, we're predicting 40 steps ahead, so that comes out to a more than 30 gigs. So it's really like pretty much like a movie that we're predicting. In terms of work, it works like similar to the model I explained before via graph neural networks, but it encodes a couple of inductive biases. The first one is autoregressive. So as I was saying, the physics of today are the same as the physics of tomorrow. That means that we only need to learn a function that from the weather today, it predicts, or now, it predicts the weather 6 hours from now. And if we want to predict 10 days ahead, well, we just apply the function multiple times. What's this function? This function consists of 3 graph neural networks. The first one encodes the information. So we go from the Earth to a mesh. One of the reasons to do that, apart from saving compute, is that this mesh is kind of uniformly divided across the Earth, whereas observations or the grid that we were given really is divided non-uniformly across the Earth, which makes message propagation very hard. The second one is this processor, where we propagate the latent states, as I was showing before, over a very particular mesh, and then we decode the information from this mesh, and we make final predictions on every place on Earth. The graph over which we make message passing is a multi-resolution mesh. So we have very few edges that go very far, and many edges that move very locally. The intuition here is that the weather today in London may be affected mostly by the weather in the UK, and not so much by the weather long range. Compared to maybe the work I showed before, where the graph neural networks were like 49 nodes, in this case, the network was 41,000 nodes and more than 300,000 edges. So it really is massive. The batch size for our model is literally 1, so we can only fit one example per TPU, and we use 32 GPUs in parallel. So it really requires a lot of engineering to make this work at scale. But the predictions are very good. So we can see surface wind, surface temperature. If you don't see differences between the top and the bottom, it's roughly the intuition of this slide. So let's look more quantitatively. So if we look at the error of making different predictions, so in this case, geopotential 500, which is kind of a different way of thinking of atmospheric pressure. Of course, both the blue, which is GraphCast, and the black, which was the best physics model, we get worse error over time, right? At 10 days, we're going to make worse predictions. But it's clear that the GraphCast has a better prediction, has lower error than HRES. So it makes sense maybe to think about the percentage of improvement. That's what we call relative score. And you can see that for this variable, we have maybe starting at 15% of improvement, and then maybe up to 10% of improvement at long range. But of course, there is only one variable. We can do that over very many variables. And there is so many variables that we really have to show them in colors. Otherwise, there would be too many plots. If the plot is deep blue, that means we have a very big advantage. If the plot is if the color is light blue, less advantage, and if it's red, we are worse. And the big picture here is that you can see that we improve on 90% of the targets, so across all variables, all altitudes, and all lead times. So in blue, GraphCast is better, and you can see maybe a pattern, which is at high altitudes we do worse, and at low altitudes we do better. This was a mistake we made in kind of designing the loss function, where we were not weighting the higher levels enough. Once we designed a better, more principled loss function, this number went up to 97%, but the model we sent to science was 90%. The second thing that I mentioned was autoregressive training, right? So you can see here that if we train the same model to do good 12-hour predictions when applied twice, or good 24-hour predictions when applied 4 times, we're basically trading off performance. So we do a bit worse on the early lead times, but we do much better on long-range predictions. So if we think about structured in machine learning, here we have shown 2 things, autoregressive and multi-scale inductive biases. And in terms of impact, maybe the algorithmic novelty or the new setup is not here. Previous works had explored this, but really it's important to emphasize how showing exciting results and really it changed the way that weather research is done. So for instance, we presented this to the European Weather Agency, which used to have essentially almost zero machine learning. And since then, really, they have started to change their cluster, which used to be CPU based. Now they have to buy GPUs. Now they're hiring machine learning researchers. So really the field is starting to change a lot with this type of exciting results that are convincing the field that this is a promising direction. At the same time, this was only deterministic weather, so only making a single prediction. What if we want to predict probability distributions? And that's what we've explored recently. As you know, it's a chaotic system. So we've all heard of the butterfly effect. So maybe you can predict the weather quite accurately 6 hours in advance. But if it's like 6 days ahead or maybe 20 days ahead, really it's impossible to predict the weather accurately. So it's fundamentally uncertain. And as I was saying, GraphCast only tells us the mean of the distribution, but not the uncertainty around it. So what we want to do is ensemble forecasting, where we predict maybe 50 samples of what the weather could look like. Each sample is going to be realistic weather. So it's modeling the joint distribution of weather across both space and time. So correlation. So for instance, it's not the same saying that there is a lot of wind in London and in Cambridge, 50% probability in London, 50% in Cambridge, but they are uncorrelated versus if they are correlated. So imagine if you have like wind turbines. It's not the same always having a bit of wind and always having a bit of energy generated than sometimes getting zero wind and sometimes getting a lot of energy. So really, we want to model these correlations as well. In practice, what we do is we implement a conditional diffusion model. So if you've heard of DALI or Imagen, these are also based on diffusion. So instead of kind of predicting images or video from text, we predict future weather from present weather. In changes with respect to the previous paper, the resolution is a bit lower because things are more expensive, but we can predict further into the future because now it makes sense to talk about the weather 15 days into the future because we're making probabilistic predictions. So in terms of implementation, it works a bit like a diffusion. So it's not the main emphasis of this talk, but essentially diffusion, how it works is by progressively noising signal into a Gaussian, and at a different time, you start from a Gaussian and you denoise the model because you've learned kind of a denoiser. In our case, it's a conditional denoiser. So it picks the current weather, and that informs how the variable should be denoised into the prediction of the day for tomorrow. We only train this for 12-hour predictions, and then the same model can be applied multiple times to make further predictions. The nice thing is that a lot of the framework, really, we didn't have to change with respect to vanilla diffusion. So in this case, elucidated diffusion models from Karas et al. At NVIDIA. Maybe one of the things that we had to change is that our metric space is a sphere, right? We are modeling weather across the Earth. It's not an image, that's a rectangle. So the noise has to be kind of Gaussian on a sphere, not Gaussian on a rectangle. And the architecture was based on the GraphCast architecture, except that the processor now is a sparse transformer, which is kind of each node can attend to neighbors that are nearby on this mesh and cannot attend to neighbors that are very far away. This has two advantages. One, it's much faster because the tension is sparse, so many fewer connections to compute. Second thing is we encode the geometry of the Earth implicitly. Now we've seen, we can see here the power of probabilistic predictions. On the left, you have the ground truth. You can see there is a bit of a cyclone here in deep blue. And if we look at GraphCast on the right, you can see that at 6 hours, so in pink, you can see that, at 12 hours, we still predict the cyclone. But if we look at forecast 10 days in advance, really the predictions are super smooth. It doesn't look like real weather at all. In contrast, if we look at the samples from GenCast or generative model, you can see that each sample prediction really does look like real weather. Once you average them, of course, it's very smooth, but each individual sample is really captures the probability distribution. And this can also be observed in the spectral power, which I'm going to talk about it in a minute. This we can compute either the MSE metric or the CRPS metric, which are different metrics on how to evaluate the ensembles. The first one is kind of more deterministic. The second one is more probabilistic, and same with prior scores. And basically, most of it we beat the best physics model in the world. Still at one resolution, at one degree of resolution, but it's very promising. One nice thing though is that we in GraphCast we had to train the model autoregressively, but in diffusion we only trained for one step, and the model just worked for future weather. So why do we think this is? Well, the first thing is that GraphCast really was predicting the predictive mean. So as I mentioned, really it keeps blurring the weather predictions more and more. So that means that the function from perfect weather to slightly blurry weather, and from slightly blurry weather to very blurred weather, really is slightly different. And so that means we cannot learn an exact function that applies every time. However, we think that diffusion, because it models the real weather distribution, it always kind of looks the same. So we can really use the same function over and over. We don't even need to train for this to be the case. As I was mentioning, GraphCast predictions really were blurred, and you can see here in pink that the power spectra really decreases, meaning we lose the high frequencies, whereas blue and black are very one on top of the other. So we are learning the spectra correctly with the probabilistic predictions. The second thing is the wind speed. So if we think about predicting the wind, sometimes the wind goes left, sometimes the wind goes right. So if you were to predict where the wind is going, on average, you would say, oh, it's not going anywhere, right? It's stationary. But if you think about now deriving the speed of this wind, you would say it's 0 kilometers per hour, which doesn't make much sense because on average, there is a bit of wind. You can see that we are under predicting wind in GraphCast, whereas in GenCast, we are predicting pretty much the exact quantity of wind. Again, if we look at the two stories, the first one about structure, now we've encoded two different types of structure. We've encoded diffusion models, which really helped model the true weather distribution. And we've talked about sparse transformers, which have a bit less structure than graph neural networks, but are a bit faster. In terms of impact, maybe the type of impact is similar to archive GraphCast, where we showed very exciting results in terms of variable predictions. So now let's look at Science GraphCast, and we were very excited to see that GraphCast was highlighted in the cover of Science 22nd of December, and there was also one of the 10 finalists for Breakthrough of the Year in the whole field of science, in entire science for 2023. One important fact is actually the model is literally the same. We didn't train a new model for 6 months. We only focused on showing that what we did really mattered to the world. So we explored severe weather. So I'm going to skip this a bit because we are running out of time, but we were predicting kind of rivers in the sky, kind of, and extreme heat. So hot in the summer and cold in the winter. And essentially the results, we showed that whenever GraphCast was making better predictions on raw variables than HRES, it was also doing better in extreme prediction. Maybe the most important one was tropical cyclones, where because of our predictions, we can deduce where the tracks of different cyclones are going. And we showed that we had around a 9-hour advantage compared to physics models. And once we open sourced the model to the community, initially the press was a bit skeptical, but the first hurricane that happened after we open sourced the weights and the predictions was Hurricane Lee. And there, the overall field of machine learning did better than physics models, and GraphCast did particularly well with multiple days of advantage compared to physics models in predicting that the hurricane was going to hit Nova Scotia. Here there are the codes and the weights, and also you can go to the European Agency for forecasts. So let me conclude. The first story is, again, structured in machine learning. So we've seen different types of structure. We've seen graph neural networks, a sparse transformer. There's people in the community that have done just vanilla transformer with several patches, like Huawei, for instance, with a paper called Pangu Weather. There's been other works at NVIDIA using Fourier neural operators. So there is really a spectra of things you could do. You could even leverage spherical symmetries that we are not leveraging. The fact that the graph that we were creating lives on a sphere, we were not leveraging that, and we could have done some things more like this. Or we could do just using vanilla MLPs. So there is really a spectra. Maybe the book that best encapsulates this that I really like is called Geometric Deep Learning. So 2 recommendations here. First, be aware of the space of the different types of symmetries and things that you can encode and not encode into the system. And also think about the trade-offs, because really you want to encode the right inductive biases, but you also want to be aligned with the TPUs, with what's really simple and at the same time fast. And finally, one point in orange here is about the fact that there's an implicit hidden bias in our data. We are training on a data set that was created using the traditional weather systems. And so by definition, there's lots of physics-based inductive biases hidden in our data. And finally, the second thing is about real world impact. So thinking about when you work on machine learning research, think about what the type of impact you want to do. And really, there is a lot of options into how you can your work can impact the world. Finally, I wanted to thank my collaborators, both in GraphCast and in GenCast. And thank you all for your attention.
Awesome. It's so exciting. We have questions. I see Eric is asking, will this work for long-term predictions?
Yeah, it depends on how long is long, because in weather there is all like many different time scales. So probabilistic predictions, we've used 15 days. We think that maybe 20 days or so, it's still reasonable. And predictions can still be used. Of course, they're going to be less accurate by definition, but can still be used. Now, there is interest in using our models to make what's called subseasonal forecasting, so predicting maybe 2 or 3 months ahead. 2 or 3 months ahead, you cannot say, oh, okay, 2 months, in 2 months is going to rain. You have no chance of predicting this. But you can predict statistical properties. So for instance, if you're a farmer, you can think about, okay, what are my chances of raining, or am I going to get an unusually hot summer and things like this. And there is interest in the community in doing this. And then because weather has been machine learning has been so successful in weather, there is efforts in climate as well, but it's less advanced than in weather, as far as I know.
Let me start with early questions. So Neeraj is asking, do you use the Laplacian to construct the graph?
No. So the graph is really so it's implicitly affected by the Laplacian. Let me see. So I'm guessing this is about the first paper.
May I ask you directly? When you create the graph, how do you decide like where you want to have higher resolution and where you want to have lower resolution?
Yeah, that's a great question. We initialize them either at random or uniformly, but then the key thing is that these node positions have parameters, and these parameters can be trained as if they were neural network weights. So you can train them on a small data set, fine-tune the node positions. I'm not sure if the video actually happened, but essentially run gradient descent on the node positions, and the nodes essentially are trained to focus implicitly on wherever it matters the most. Usually whatever is most useful is usually on the harder places. But if for some random reason it's better to put them in some other structure, then so be it. The big thing is that the network decides where to put them.
Your graph neural network is doing two things, right? So first, it's deciding like, what difference equations it needs to solve. And then the second thing it's doing is it's estimating a numerical solution to those equations, right? So what if you just decompose it explicitly? And, when you're learning this mesh, you're basically learning what equations to solve. And then you solve the equations using like traditional techniques. Have you tried that? Like, what kind of performance do you think you would get if you weren't also using the neural network to do to estimate the numerical solution?
We haven't done that, but there's other teams that have explored some directions like this. So, for instance, another team at Google, I was not part of this paper. It's called Neural GCM, and they couple the kind of a solver of the basic weather equations with a machine learning part that corrects these predictions. And the intuition being that there's a few governing equations of weather that really drive most of the weather, and then there's only a few things that are not correctly modeled by those equations, and then maybe we want to learn those. And they showed promising results there. Two things that so I really like that paper, and really they do an amazing set of evaluations, so I really recommend it. So why we didn't do that? One, it's slow, right? So here we're leveraging the power of GPUs or TPUs in our case to really make massive compute that goes very, very fast. And so usually when you have a traditional solver, it's a bit slower. The second thing is that machine learning often just cares about give me the most direct, like the raw problem, and then I'm going to find you a solution. And every time you decompose the problem, sometimes you lose a bit of inefficiencies by decomposing the problem. Sometimes if your decomposition is really clean and really well made, you have data efficiency gains, and there is an inductive bias to be made there. If there is a lot of data, like in the case of weather, because really there is a lot of information about the weather over the last 50 years, the data set is massive, and then it really pays off to tackle the problem directly.
Do you think that your latent representation is also capturing a lot of like information about the numerical solution besides just the configuration of the nodes? That's basically like what you're saying, right?
Yeah. So just to be clear, the GraphCast and GenCast papers did not train the nodes. We've seen similar things in for instance, we can observe the gradients of the function, and we see that the gradients make sense. So for instance, you can imagine like you can backprop the temperature in California today, California from 5 days from now, and backprop it to the temperature anywhere on Earth and see what temperature, where on Earth affects the temperature in California, and really is affected by the places one would expect. We have not looked into the interpretability of the latent space, though.
Dmitry is asking, sounds like you use the surface data. Have you considered using the signal from deeper ocean?
That's a good question. So yeah, we use surface and atmosphere. We have not used the ocean. We have started to use, actually GenCast uses a variable called sea surface temperature, exactly, which just is the temperature just on top of the ocean. And this helps. Now, you could also model the oceans, but that's kind of its own problem. So, for instance, before we were talking about subseasonal prediction or climate predictions, some people say, assuming I know the temperature of the ocean at any point in time, are my weather predictions reasonable? And so they cheat for scientific purposes and assume this and check whether their scientific predictions make sense. So far as I know, no one has tried model building with a pure MLM model entire thing. That would be an interesting direction.
Some technical issues what this haven't done before. It's just like it will be done. There's no like serious.
I think the biggest thing, if I would say, it's probably data. I don't know. We have the data. Like it may be there is someone that has the data, but at least our team, I don't think we have it. And at the same time, it affects the weather, but it does not affect it so much that you cannot just do weather prediction without the ocean as well.
I was wondering because in GenCast you mentioned this sparse attention to get the prediction in every node, like at every point in the surface, right? Where every point just attends to the neighboring nodes in the graph, right?
Yeah.
So then I was wondering if in GraphCast, to do the prediction at every point, do you attend to the entire world?
That's a good question. So in GraphCast, what happens is we use this mesh, which is a union of all meshes, but you can see like most nodes. So there's only a few nodes that have very long range connections, and then we kind of subdivide and we kind of keep creating more and more nodes. But very few nodes attend to long-range positions. Most nodes only attend to their immediate neighbors. So think about like every node usually looks at kind of maybe 6 nodes nearby or something like this. A few nodes look at the 6 node nearby and 6 nodes that are a bit further away. Sorry, I say 6, but I think it's 5. Yeah, and then so on and so forth. So most of the nodes in GraphCast really mostly look at 5 other nodes or things like this.
Do you have like for the let's say like there's long range attention, do you have like some extra bias that you add there, like some sort of like distance weighting or something like this? Yeah. Or
we've talked about it, but we haven't tried it actually. Yeah, that's one of the things that it makes sense, right? There is some direction, some connections that if it's longer range, you should expect to kind of lower weight them. One good thing is that the model does know the position of every node, so it's not like so it knows the geographic position, so it can say, okay, I'm going to attend more to you because you're closer in space.
Are you familiar with the notion of stochastic optimal control?
A bit, but because I think it comes up in robotics, but and I used to do robotics, but it's been like 10 years almost.
I mean, the general idea is, right, like I've got some kind of a process that's going along, and I am an agent of some kind, a person who has to make a decision. And I can make certain changes at any point in time. Often, you look at this as a single period problem, and that makes it an easy thing to solve. But when you turn it into a multi-period problem and add stochasticity to the process, and switching costs, right, for each decision, it becomes harder. You can kind of approach it using finite differences on a partial differential equation, but like the dimensionality really kind of explodes on you. And I guess the question, it only struck me during this talk that deep learning might be applicable. Are you familiar with any work that Google might be doing on that sort of thing?
I don't know in general. So there is teams at Google that work on control outside of the weather team. Weather team does not work on control, but there is teams on like robotics and reinforcement learning and this type of thing that they do some type of control. Like for instance, the work that comes to mind that's still related to science is the fusion team. I think had to kind of model how to control tokamak plasma, and I think they were learning neural networks and kind of using some of that. So maybe some of this work can be related. In terms of kind of more closer to our work, we know that we can use the gradients of the networks to kind of optimize stuff. So we could think about in the same way that before I talked about node positions. In node positions were optimized to lower the loss function and make better predictions. It's possible that we can use that for instance, sensor placement and things like this. But honestly, it's a very wild hypothesis. And I've heard it in workshops, but there's still a lot of research to be done.
My question is related to Borja's question about like the sparse attention. So I'm guessing this happened like in the diffusion, like similar, like you gave an analogy to the diffusion process, right? You take individual steps and denoise the input. So when you use sparse attention, does the same thing apply? So if you have more time steps during the diffusion process, like Z1 to Z, like 1 to N, right? If you increase it, does it mean it attends more globally and does it get better predictions?
Yes. There is actually two time steps kind of. So I'm not sure how, like it's a bit tricky to call so basically, so if you think about a single layer of attention, a single layer of the network, there is a sparse attention. So every node only looks locally at its neighbors. But as you know, we have deep networks that I think are like maybe 15, 16 layers. I forgot exactly how many layers. So there's going to be implicitly global communication because we have multiple layers. So you talk to your neighbors are going to talk to your other neighbors, and eventually your information gets propagated, even within a single function call of the neural network. And as you're saying also, if you apply multiple diffusion time steps, everyone influences everyone. So it's not like diffusion and a single neural network cannot inform like weather in California can still influence the weather in Tokyo or in London. It's just that the way it's going to do it, it's going to be biased to be a composition of local influences.
I understood the discrete, the first neural network which operates on the discrete predictions, right? When you go to the probability, you mentioned that you take the input, right, and then you predict a function which is like probability distribution, and then probability distribution of the weather, and then you forecast it, right? And then when you want to predict for the next day or the next time step, you take the prediction and use that as input. So during the first, like the current weather, how do you convert that into a probability distribution? Because I'm guessing it's like a function to function transform, right? But currently we have a discrete temperature. We don't have a probability.
The idea is that we do not output probability distributions. What we output are samples from the probability distribution. So in the same way that when you ask Imogen or DALL-E for an image, it only gives you one image. It doesn't give you, I don't know, all the, like if you ask for a cat in Manhattan, it doesn't give you all the images of cats in Manhattan. It gives you three samples, 3 images. We give you also 3 weathers. And from that, we give you 50 weathers, and from that you can just reason about, okay, like out of the 50 samples that they gave me, 20 gave me a probability that I'm going to get hit by a cyclone, so maybe 40% chance that I'm going to get hit by a cyclone, maybe I take cover. So same here, we take the weather today, and the diffusion process is going to give us a single sample of the weather tomorrow. Then we take this sample, and then we get a sample for the weather 2 days from now, and so on and so forth. But it's all samples. There is no kind of
Got it. You get the uncertainty by getting more number of samples and looking at the distribution.
Yes. If you want more exact, you can go much. One nice thing about this that I didn't talk about is really the physics models take an entire data center 2 or 3 hours to predict the weather. So because we can make predictions in a matter of minutes, really we can generate many more predictions compared to physics models. So that's also going to be an advantage of machine learning.
I'm very interested in the physics-informed aspect of the neural nets. So the first thing I would like to know is about the loss function. You mentioned that between the science paper and now the GraphCast has a refined loss function and that improve its performance. Could you please elaborate on the aspect of that refinement and if more physics has been incorporated?
Yes and no, but I also have an so let me answer in two parts. So what I mentioned was that the loss was more principled. So whether, as we can see in this slide, it's really massive number of predictions. So for those familiar with multitask learning, it's a massive multitask learning. You have to care about thousands of predictions at the same time. So really, it's about a trade-off. You say, okay, I can do better in surface, but I'm going to do worse in the top of the atmosphere. If I do better on the top, I will do worse in the surface. So we really set the weights of the loss function a bit. We invented them and with a simple formula, and we left them at that. And then at some point, we discovered that that was suboptimal. We then thought about, okay, what's a good loss function to design? And we realized that the best weights of the loss function was the inverse error of our baseline of the physics model. So for two reasons. So if you think about it, the error of the physics model, if we divide by this, it's literally optimizing the colors of this slide to optimize so that everything is blue and you care about all squares equally. So when you divide by the error of the HRES of this physics baseline, you say, please make me this slide blue as possible. That's pretty much what you're asking. And so that makes more sense than whatever other function we design. The second thing is that the physics model, when it makes a mistake, usually it makes reasonable mistakes. So if it makes a mistake like imagine I say, okay, is making a 4 degrees Celsius error in a 24-hour prediction? I don't know. Like maybe it is reasonable, maybe it's not reasonable. Is it reasonable to make a 3-meter error in geopotential? We don't know. But because the physics model has we can look at the errors of the physics model, and we know that these errors are reasonable. It gives us an estimate on kind of the irreducible noise. It gives us kind of an upper bound on the noise. And so dividing by this, it's also well defined from a maximum likelihood perspective. This is not encoding physics in the way that you're asking, but there is two lines of work that I know that are maybe a bit more related to this. So I know that people have used physics-informed neural networks, which are neural networks that use literally impose the laws of physics in the predictions to, for instance, do data simulation for cyclones. And another thing that I've worked in the past is you can train neural networks either via auxiliary losses that can be used at training time, but also at prediction time to impose certain constraints that you know that the physics satisfies. So for instance, if you know that there's a conservation of mass or a conservation of energy, you train the model to say, make me predictions, but at least satisfy these basic laws of physics, and that this usually improves prediction quite a bit. We didn't try in this model, but that's something that I'm pretty interested in.
I may follow up with you offline in terms of this loss function, because I do think that it's very interesting to optimize for specific cases. I just think that this may be case by case, because the physics model may be mistakes not in a general way. Some in certain conditions it may make more mistake, in other conditions it may be performing better. So if you are calibrating against the physics model, you might end up falling for that as well.
That makes sense. Yeah, feel free to send me an email and we can follow up.
Oh, I see a question from Paul. What kind of data would be helpful to improve the model? Something
that is known in the field is that we are using what's called reanalysis data. So basically, if we think about how the real weather works, a weather system, it's basically there is weather stations, there is like balloons that we send to the sky, there is satellite, and there's going to be lots of sensors. And then someone has to go and say, if given these sensings, what's the weather anywhere on Earth? And so what usually happens is we kind of accumulate sensings during 6 hours, and then we say, okay, given the sensors, the weather, not now, but 3 hours ago, that's what the weather was 3 hours ago everywhere on Earth. And from this, we make predictions. And that's actually what we use. So implicitly, when we say that DeepMind is predicting the weather 10 days ahead, it actually also needs, of course, the sensors, but it also needs a physics model that accumulates these sensors and makes this initial estimate of the present. Now, one thing that the field is asking is, can machine learning also help with going from the raw sensor observations to this initial estimate of the weather? And I think that's an interesting direction for the field.
So can graph neural networks be used to construct, basically can be used not for weather predictions, but for like other fields? In this case, a person is asking, could be applied to healthcare and basically construct a representation of patient data, linking different types of data like CT scans, like temporal breathing patterns, like time series data, and biomarkers, like a tabular data.
One has to think deeply about the problem. Like there's going to be things that, like some of these things set in this list, probably the answer is yes, and the answer in the other one, some of them are probably no. In the sense that I think overall the problem has to look like a graph and be modeled naturally as a graph. So I think, like, for instance, thinking about like COVID spread or things like this, maybe thinking about graphs dynamics here makes a lot of sense, and kind of, whereas some others, like depending on the definition of a CT scan, if it's like the image or the raw sensor versus like connecting all the information from a sensor to like different kind of analysis to a single patient, one has to think quite carefully about this. I would recommend the book I mentioned towards the end. It has a good analysis on graph neural networks. Let me see if I can find the paper. Yes. So this book, I think, has a good overview of graph neural networks, but also other things. I think the graph neural network part is pretty complete. Maybe that's a good start on like what things can graph neural network do and cannot do. Overall, yes, they have lots of applications.
You know, also we have, like, our community is like quite diverse, and we have researchers, engineers, and like computer science students. And very often they ask, you know, how I can get into machine learning. I mean, considering that you're working with, you know, like top AI research company. And I see actually on this call, there's a David Sanchez. Actually, with him, we discussed this question also on our happy hour. Like, what would be your recommendation for those who are, you know, students or developers and want to get into like serious AI research? What you would recommend them to do?
Yeah, thanks for the question. So I think overall there's two things that if you want to get into research you want to do. One is acquiring the knowledge, and the second one is acquiring the mindset, I would say. In terms of acquiring the knowledge, I think that's not how I did it, but that's kind of more how I'm doing it right now, is through YouTube. There's really lots of interesting talks, like for instance this one, but well, not this one, but like this series. But really there is lots and lots of content out there, right? And a nice thing about YouTube is that you can also speed it up, you slow it down, stop it whenever you want, and combine it with other activities. So that's really how I consume a lot of my knowledge. The second thing about the mindset is twofold. The first one is thinking about what your skill set before the research you could bring to the table. So like, for instance, I come from math and physics. It's not super surprising that the type of research in machine learning that I'm doing is kind of more physics-based and mathematics-based than the average, because I think that's where my passion was and also where my skill set are. But there's other people that are very, very good engineers, and maybe they do machine learning engineering connected to the research, like there's research engineering roles at DeepMind, for instance. So really thinking about this. And the second thing about the mindset that is really critical in research more than in many other fields is learning how to ask questions and really questioning everything. I think it's very important. One way to train this is when you are learning things, it's important to be really questioning everything. And so asking yourself questions, trying to answer them. And then if you don't know the answer, or even if you think you know the answer, asking another friend or asking Gemini or other AI models to get the true answer. And so training yourself to question, I think, and to build a deeper understanding.
And also, like we discussed this with you before, Ferran, and I also like what you mentioned, that implementing like make open source versions of papers, right? Like to showcase your skills. I think that also could be helpful, right?
Yeah, exactly. So the other thing is, okay, so one thing is kind of being training to be a researcher. And the second thing is getting hired as a researcher. That's kind of the second step.
That's the ultimate goal, to be hired as a researcher.
Like, people are aware that there is lots of ways to build the skill set, because again, the knowledge is open now. So it's not like you have to do a PhD. But you have to build a CV in the same way. So there's either open source, I think, or publishing in conferences. To me, that's the two most clear ones. And then being aware of the opportunities. So there's lots of famous companies, big companies, but there's lots of startups as well. So or academia. So being aware of all the different places and building a kind of a curriculum is something I'd recommend as well.
A question from me. It's sort of off topic, but since we're like kind of nerds, I'm really curious to learn like what kind of book you would recommend, or maybe like interesting games that you recently discovered, like some interesting projects that I think nerdy people like us would be excited to read or try.
Yeah. So a book I read last year that I really liked, it's probably well known, but it's called Project Hail Mary. It's a science fiction book, and probably the first chapter was probably the best chapter I've ever read, but it still doesn't kind of go down from there. So I really recommend this book. And maybe a game to which I have a funny story is like it's a game called Blood on the Clock Tower, which is a bit inspired by Mafia or Avalon, this type of kind of social bluffing and social deduction games. They prototyped it at MIT. So the inventors are from Australia, but they brought it to MIT, and really they had to create a rule that, because there was at MIT CSIL in the computer science department, we used to have board games every Friday, and people only wanted to play this game. So we had to make a rule of only playing it every 2 weeks. So one week we played Blood on the Clock Tower, the other week we played every other game. And so now I bought it for my friends, and they all really like it.